Welcome to Physics 2211, Lab 1, Constant Velocity. In this lab, we're going to measure the observed motion of an object at constant velocity using Tracker and compare those results to a computational model using GlowScript. Hopefully this will demonstrate the principles of Newton's first and second law. In this experiment, we'll use a lacrosse ball rolling on a hardwood floor. To get a ball rolling at a constant speed, we first need to understand what inertia is and how a force affects it. Inertia can be described by Newton's first law, which states an object at rest remains at rest, and an object in motion remains in motion at constant speed in a straight line unless acted on by an unbalanced force. This means that in order to maintain a constant velocity, the net force must be zero. We can prove that by rewriting Newton's second law as the velocity update formula, and that this shows that the net force must be zero for initial velocity to equal final velocity. We also will use the position update formula in our calculations. Here's a free body diagram explaining the motion of the ball. To get the ball rolling in the beginning, we will need the net force to be more than zero. We'll have to use an impulse, an initial force, to accelerate the ball to a velocity that then will hold at a constant velocity by not applying any more force to it, which is in accordance with Newton's first law. Our procedure will start by recording the lacrosse ball rolling at a constant speed by applying a temporary impulse, and then we'll import that video on the tracker and record the point masses frame by frame. And then we're going to use a GlowScript Python command to create a computational model using the initial conditions from that experiment. And then we can import the position time data from both of these programs into a spreadsheet and compare the data with a graph. Now that the video has been recorded, I imported the video into Tracker. And in here, I can set the origin at the center of the ball, and then I've used a measuring stick in the background as a calibration tool. And then I'm now going to track at every single frame the position of the ball. And this is what it looks like. So here I've calculated it at 90 frames. For the computational model, we're using a program called GlowScript. In the initial conditions section, I can set the system mass. For the lacrosse ball, I have measured 143 grams. And then for the initial conditions for position and velocity, I'm using the data collected from Tracker. For time, because the video in Tracker was done with 60 frames per second, I will also be calculating data at that same time step. For the calculation loop, I have everything within a while loop. And this allows for the calculation to happen at every single frame per second, just like Tracker does. For the net force, based off of our whole idea of keeping a constant velocity, we don't want to apply any more force, so we're using a net force of zero as our predicted model. And then for the calculations, we are basically converting the velocity update formula and the position update formula into code. And now we can run the program. Now that we've compiled our data into a graph, we can see that the observed position, highlighted in blue, starts to diverge over time from our simulated model in GlowScript. This means that unlike the GlowScript with a net force of zero, there must be an outside force acting on our observed position. Possible errors could include outside forces such as friction and air resistance, which can include like the hardwood floor and the air within the room acting on the lacrosse ball. And when it comes to our data collection, our position tracking could be affecting it because of the manual placement of point masses at the center of the ball. And as well, the camera itself has a distortion as you go to the edge of the screen, so that can also cause some error. Now it's time to dive deeper. How would the result be affected if the positive x and negative x axis were interchanged? Well, the result will remain the same except for the slope of the graph being flipped to positive. Is it possible for you to say how many pushes and pulls are being added together to give zero net force in the case you observed? Because of the deviation in the observed position, there must be outside forces influencing the change in velocity. However, the number of pushes and pulls cannot be determined, only its net effect. This is because there's more than one input of values that can give the same output of values. Thank you.